In this video, we'll do a few examples of problems that you have to solve for a nuclear power plant. So for this problem, we have, we're going to assume that the average power consumption for a house is 500 watts. So we want to know how much uranium-235 we would need, all right, to supply this household with electrical energy for an entire year, all right? So assuming the house is continually using 500 watts for 24 hours a day, 7 days a week, all right, 365 days a year, whatever, however you want to say it. All right, remember that power is equal to energy divided by time. All right. So in this case, our 500 watts. All right. Right here. If we want to find the energy, oops, there we go. We just have to multiply power by time. So the time here is going to be 1 year. So it's going to be 500, all right, joules per second times. Do the conversion. It's 31,536,000 seconds. Thank you, Rent, for reminding us of this. There we go. And this is how many joules we have in a year. All right? So what we can assume, all right, is 100% efficiency, just for the sake of this problem, in converting between fissionable energy and electricity. Okay, so if we do that, we know, right, that the energy density, also we have to look this up on the table, this is a piece of information that we would need here, it's going to be this, and okay, how do I know I need energy density? Well, what is it that we're asked to solve for? I didn't write it before, but we are asked to solve for what the mass is, okay? So that, typically is going to, tell you that we'll need the energy density because it's like a conversion rate. It's like currency, all right? We're going from dollars to euros. Dollars being joules, and we'll say euros is kilograms, all right? And the exchange rate is going to be the energy density. So we have what we're looking for in the units there. We know what we want. That's how we know to use this, okay? All right, so given a certain amount of energy, if we take this energy and divide it by the energy density, right, that will leave us with the mass. So, in this problem here, all I need to do is take our 1.577 times 10 to the 10th joules, divided by this ungodly number for the energy density for uranium. And we see that for one household, all we need is 0.175 grams. All right? And when we get the units out like this, it looks like that. All right, very small amount of uranium to power a household for an entire year. It's pretty cool. All right? So let's take a look here at another question that you might get on an IB test. All right? We got this fission reaction right here in a nuclear power plant. We'll say that this is the one that happens. And let's see, we're going to estimate that the initial amount needed to operate, what we want to do, is estimate the amount we would need to operate this reactor for 1 year, assuming 40% efficiency, okay, and assuming that 200 megaelectron volts are released for each fission reaction, all right? So, really quickly here, if we look at the mass of uranium-235, this is something that we would end up needing for an example like this. The reason being, okay, is that we're looking at the energy density, okay, and so we know the energy per fission, so we should know really the mass of the uranium because there's one uranium atom per fission. All right, you'll see how this works out in a little bit. So to begin with, the mass of uranium-235, if you look it up in the table, is 235.0439. Really long, boring number. Oh my gosh, how many are you done? There we go. Okay, unified atomic mass. What this converts to, okay, is in kilograms 3.902996 times 10 to the negative 25th kilograms. And we do want it in kilograms because of our energy density. All right, so the power output in this case is going to be 600 megawatts. Our efficiency is going to be 40%. All right. The power inputs is going to be the output divided by the efficiency, and in that case, it's going to look like this, 0.4 since it's 40%, all right? And so that means our output, excuse me, our total input from the fission reactions is going to be 1.5 gigawatts. So the entire energy that we're going to be using in a year, if this is what the power plant is continually putting in, okay, that energy for a year, again, is just going to be power times time, exactly as it was in the previous problem. And what we end up with here, we're going to switch this to scientific notation. There we go. And there we go. Our rent time, of course. And from there, we end up with 4.73 times 10 to the 16th joules. All right. So this is the total amount of energy that we would need in a year. Okay. How does that compare to the number of fissions? Well, let's look at this. If we know that we have a certain total amount of energy here, and divide this by the energy per fission, okay, we'll get the number of fissions. Okay, so when you do that, where did I get that 3.2 times 10 to the negative 11 joules? One other calculation that I have not shown here, I'm going to show really quickly. We know that there are 200, the energy per fission here, there are 200 mega electron volts per fission, all right? And so what I did here is I just converted using my 1.6 times 10 to the negative 19 joules per electron volt. Okay, and that's what gave you that 3.2 times 10 to the negative 11 joules, okay? So this tells me how many fissions there are, and really quickly, all right, I just kind of skipped over that. It's just down here. Okay, the number of fissions is going to be equal to 1.48 times 10 to the 27. All right. So what we assume is that every single atom of uranium-235 here is going to fission. Okay, that's one of our assumptions. And if that is the case, all right, we're going to take that number of fissions, multiply it times the mass, all right, of a single uranium nucleus, or atom, excuse me, and we get the total mass of uranium that we would need as being about 600 kilograms of uranium. So that's for an entire power plant for a year. That's not even a metric ton, okay? That's rather incredible. So there's an extra problem there. On the next page that deals with breeder reactors, what I want you guys to do is to read over this, okay? And come to class prepared to talk about it. We will be taking a quiz in class on this type of problem solving, okay? So also please read over the safety issues and risks in the production of nuclear power. We'll be testing on that as well, okay? For now, I'm going to finish this video. In the next video, we're going to talk about nuclear fusion and do some practice problems with that.